Now we're going to be looking at rational functions and their graphs. Let's recall what a rational number is. A rational number is any number that can be written in a fraction. Okay, now remember that can include whole numbers because we can always write whole numbers over 1. Now a rational function is a function that can be written as p of x over q of x, where p and q are both going to be polynomial functions. Now remember, the bottom of a fraction can never be 0, so q of x can never have values of x that make it 0. So here is an example of a rational function graph. Here's the rational function, negative 2x over x squared plus 1. Now this is what we call a continuous graph. Now being continuous means there's no jumps, no breaks, no holes. I can draw the entire graph without picking up my pencil. So it's a smooth curve, there's no breaks, and I do not have to pick up my pencil to draw the rest of the graph. Here is another example of a rational function, 1 over x squared minus 4. Now this is what we call a discontinuous graph. Now if you notice, if I'm tracing the graph, I have to pick up my pencil to go to the next section of the graph. So discontinuous graphs mean that there's some points of discontinuity. Now looking at this graph, what values of x can I not have? Well, if you look at the original function, y equals 1 over x squared minus 4, I can factor the bottom into x minus 2 and x plus 2. So remember, our denominator can never be 0. Well, what values are making my denominator 0? Well, x equals 2 and x equals negative 2 are causing me to have issues. Well, if you look in the graph, I just happen to have asymptotes at those values. That is what is causing this to be a discontinuous function. Now you can probably also see another asymptote here, and it's going to be the line y equals 0. So we can have two different types of asymptotes, horizontal and vertical. Here is another example of a rational function. Now the equation looks like a rational function, but when you look at the graph, it looks like a line. Now the reason for this is when you look at the equation, you can see that I have an x plus 2 on the top and an x plus 2 on the bottom. So what's going to happen is that these are going to divide out and leave me with 1. So I'm just going to have y equals x plus 3. Well, the graph of y equals x plus 3 is just a line in the form y equals mx plus b. Now, why does this graph still look a little different? Well, I have this hole right here at negative 2, 1. Now, where did this hole come from? Well, remember, in our rational functions, we cannot have the denominator ever be equal to 0. And if you look at this function here, if you set the denominator equal to 0 before we divide it out, you would get x equal to negative 2. So the point x equal negative 2 is going to give me issues. So to represent that in the graph, we draw a hole. So think about your inequalities whenever we graphed inequalities. So say I had x greater than 2. When I graph that on a number line, I would put an open dot on 2, and then I would shade to the right. That open dot symbolized that my function does not exist there. And that's exactly what's happening in this graph. So this is still a discontinuous graph because I have to lift up my pencil to jump around this hole and then keep going. A point of discontinuity is going to be a number a that makes my denominator equal to 0. Now, there are two different types of discontinuities. We saw one type in this type of graph, and we saw the other in this rational function graph. The first type of discontinuity we're going to look at is called a removable discontinuity, or as I referred to it as a hole. Now, a hole occurs whenever we have a term that is in common on the top and the bottom of a fraction. So in the numerator and the denominator, I have a common factor. So this function that we looked at earlier, the x plus 2 occurs on the top and the bottom. So I have that same term in the numerator and the denominator. Therefore, they can divide out, and I get the reduced function y equals x plus 3. Well, the function y equals x plus 3 is a continuous function. Therefore, I removed the discontinuity. Now, if I want to figure out where this hole occurred, I take the term that was giving me issues in my denominator. So it's going to be x equal to -2. And then I take that x equal -2 and I plug it into my reduced function. So I plug in the -2, and this will give me the y coordinate to my hole. So the hole is occurring at -2, 1. Non-removable discontinuities, or asymptotes, are when the numerator and the denominator have no common factors. Therefore, the discontinuities cannot go away. Okay, they're going to have to stay there, so I have to deal with them in my function. So we represent that in our graph using asymptotes. Now remember, we have two different types of non-removable discontinuities. A vertical asymptote is an asymptote that will occur whenever we have values of x in our denominator that cannot be divided out. So vertical asymptotes are values that make our denominator equal to 0. Now you can see these represented right here in this graph. So we represent vertical asymptotes with the equation x equals a number, and these x values are x values that make my denominator equal to 0. Now in our graph can never ever ever cross over vertical asymptotes. The other type of asymptote is a horizontal asymptote, which will be a horizontal line of the equation y equals a number. Now for rational functions, we can have only one horizontal asymptote. So I may not have any at all, but if I do, I can have at most one. Now vertical asymptotes we saw can occur at any value that make the denominator 0, so I can have more than one of those. Now the other difference between horizontal and vertical is that horizontal will describe the end behavior of my graph. Therefore, at some middle point of my function, I may cross over my horizontal asymptote, but vertical you can never ever 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 cross. To find the horizontal asymptote, we compare the degree of the numerator and the denominator of the original function. So you must be looking at the original function before anything divides out. And when we say degree, we mean the highest exponent on that polynomial. So we're going to look at the numerator, we're going to find the highest degree, the highest exponent. We're going to look at the denominator and we're going to find the highest exponent, and we're going to compare them, and that's going to tell me into which case it falls into. So whenever you compare the degree of the numerator and the degree of the denominator, and the numerator is less than the denominator, that means we have a horizontal asymptote at y equals 0, which is the x-axis. So looking at this function here, the degree of the top is 1, the degree of the bottom is 2, therefore the top is smaller than the bottom, so we will have a horizontal asymptote at y equals 0. Now if you look at this graph here, you can see that the function crosses over at -1. So remember, we can cross horizontal asymptotes because they only tell us what's happening at the very ends of our graph. When we compare the degree of the numerator and the degree of the denominator, and the numerator is larger, then we will have no horizontal asymptote. So in this case, we will not have a horizontal asymptote at all. Now that does not mean it will not have any type of asymptote, but we will not have a horizontal asymptote. The last case is when we compare the degree of the numerator with the degree of the denominator and they are equal. So if you look at this function here, the degree of the top is 1, the degree of the bottom is 1. Therefore, the degrees are the same. Now in this case, we look at the coefficients of the leading term. So remember, the leading term is the term with the highest degree. So that's these two guys. And if you look at this function, the coefficient of the top one is 1, the coefficient of the bottom one is 1. Therefore, our asymptote will occur at 1 over 1, which is just y equals 1. So this function will have a horizontal asymptote at y equals 1. So when the degree of the numerator and the degree of the denominator are the same, you look at the coefficient of the term that has that highest degree, and that will be our horizontal asymptote. Finding the x-intercepts and y-intercepts will help us graph these functions later on, so it's going to be a key piece of information we want to find. Now to find the x-intercepts, and that's where y equals 0, we're going to factor and simplify, and then we're going to set the numerator equal to 0. Now, why the numerator? Well, we want y to be equal to 0. Now, values that make the bottom 0 will not make y equal to 0. It will make y undefined. Therefore, we only are going to care about the values that make the numerator 0. And then we're going to solve for those values, and that will be our x-intercepts. Our y-intercepts are going to happen whenever x is equal to 0. So for those, that's pretty simple. We're just going to plug in 0 for x after we've simplified, and any values that we get are going to be our y-intercepts. So if you look at this function, if I want to find the x-intercepts, I would first factor and simplify. So factoring and simplifying, I see that these are going to divide out, so I get y equals 1 over x plus 3. So to find x-intercepts, I set the numerator equal to 0. Well, I can never have 1 equal to 0, therefore I will not have any x-intercepts for this function. Now for y-intercepts, we set x equal to 0 everywhere I see an x. So I'm going to have y equals 1 over 0 plus 3. So I'm going to have a y-intercept at 0, 1/3. And that will be my y-intercept, and I will have no x-intercept here. The domain for these rational functions will be pretty easy. It's going to be all real numbers except for the values that give me problems, which are going to be any of our points of discontinuity. Now this will include holes and asymptotes. So any value that is a hole or any value that's an asymptote will not be allowed to be in my domain. Now the only really important thing that you remember is that you need to check domain and range before and after you divide out common terms. So if you look at this function that we just factored, before we divide out, we see that the bottom is giving me trouble at 2 and -3. So I know that these are going to be issues in my domain. And then once we divide out, we can see that I still have that -3 giving me issues. Now because this guy is a hole, I will not be allowed to have 2 in my domain, and I will not be allowed to have -3 in my domain because -3 is going to be an asymptote. So bringing this all back around, I want you to remember our reciprocal function here, f of x equals 1 over x. And I want us to compare the knowledge that we now know about rational functions to this function. Now, the horizontal asymptote of this function is y equals 0. Now think about what we just learned. The reason why the horizontal asymptote is y equals 0 is because the degree on the top is going to be smaller than the degree on the bottom. The degree on the top is 0, the degree on the bottom is 1. Now this function will not have any holes, which you can see in the graph, because I do not have any terms that divide out. I do have a vertical asymptote. The vertical asymptote is going to be at x equals 0 because that is the value of the denominator that is giving me issues here. And my domain, well remember our domain was x could not be equal to 0. And why? Because that's the value that makes the denominator 0. X and y intercepts? Well, for our x-intercepts, we set the numerator equal to 0. Well, 1 cannot be 0, so I will have no x-intercepts. And y-intercepts, we go ahead and we plug in 0 everywhere we see an x. Well, for this function, I cannot plug in 0 on the bottom, therefore I will have no y-intercepts. And this is all information we already know because we know what the graph of this function looks like. So go ahead, I know it's a lot of information, but try it out on this function here and find the horizontal asymptote, any holes, vertical asymptote, domain, and x and y intercepts.